Hi, George Diamond here again. We're looking at our video number 2, related rates. Now this is, in our textbook, this is section 2.6. So we use the Larson textbook, so we're right at the end of the unit here, so at the end of chapter 2. And this is video number 2. Now in video number 1, we talked about related rates. We looked at a couple of simple examples. We showed a 6-step process that we can use to work most related rate problems, right? The first one started off with first step is start off with a diagram or a drawing of some type. Now we have my drawing up here for the first problem. But let's take a look at we're going to look at several applications, so about 4 problems here in this little video. So we get started. Now this is actually example number 2. Example number 1 was on the previous video, but this is example number 2. Here's we get started. This involves ripples in a pond. Now it says ripples in a pond form concentric circles. So you see here concentric circles. It's a circle within a circle. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. Okay, when the radius is 4 feet, at what rate is the total area A of the disturbed water changing? All right, now remember our steps. So we start off with a drawing. All right, so I've got my drawing here. So you can see my concentric circles. It's just simply a circle. The next thing we need to do is find out what information do they give us in this problem. So what are we given? So let's come up here. Let's list our given information. Now, in just a moment, I'll be taking this this problem down and setting it out aside. So if you need to write it down or something, you want to go ahead and write it down now. Let's see what all we're given. So this problem, first of all, says that the radius r of the outer ripple is increasing at a constant rate of 1 foot per second. So in this problem, the radius r is increasing. That's the rate of change of the radius over time. Right? So we'll say dr over dt is equal to 1. This is 1 foot per second. Okay, what else do they give us? It says when the radius is 4 feet, at what rate is the total area of the disturbed water changing? So when the radius is 4 feet. So they're also telling us that r is 4 feet. So they give us this information also. So they give an information, they tell us the rate of change, or describing the rate of change of the radius with respect to time is 1. When the radius is 4. So the radius is 4. Let's see what it is we have to find in this problem. So what do we got to find? Now it says, at what rate is the total area A of the disturbed water changing? So we're looking for the rate of change of the area. So we're looking for, we're going to describe the rate of change of the area as dA over dt. Okay, that's what we're looking for here. Now, so in this problem now, we need a formula or an equation that's going to relate the radius of a circle and its area. Well, obviously, what about the area formula for a circle? Pi r squared. All right, so let me erase this here. All right, so the formula we're going to use, or the equation we're going to use that's going to relate the area and the radius of the circle is simply its area formula for a circle. So A equals pi times the radius squared. So we're going to use our area formula for a circle. And we've got our given information. We know what we have to find now. So to start off, let's go and find our derivative. Let's take the derivative of our area formula with respect to time t. Now remember, when you take the derivative with respect to time, it's actually implicit differentiation. So you're taking the derivative with respect to a different variable here, with respect to time t. So you take the derivative of a with respect to time will be dA over dt. Now, when you take the derivative of pi r squared, this will be, once again, bring the 2 down. You're going to subtract 1 from your exponent. It will be 2 pi times the radius. So 2 pi r, and then you're going to multiply by dr over dt. Now, so as you take the derivative of the area formula, this is it. So dA over dt, so the rate of change of the area with respect to time is equal to 2 times pi times its radius times the rate of change of the radius with respect to time. Now, after this, once you get the derivative of your formula, if we're given all our information, all we have to do now is substitute in and then evaluate, and that should give us the rate of change of the area with respect to time. Now, I'm going to set this here off now. Once again, we're looking for dA over dt. dr is 1 and the radius is 4. So dA over dt is going to equal 2 times pi, so the radius is 4, so substitute 4 in for r. Now dr over dt is 1, so substitute 1 in for dr over dt. And now it's just a matter of solving for dA over dt. So in this case, dA over dt is going to be equal to 2 times pi times 4 times 1, which is 8 pi. All right, so the rate of change of the area with respect to time should be 8 pi. Now this should be in feet per second. Feet per second, there you go. So it'd be 8 pi. Now if you got a calculator, you can convert it to a decimal if you want to. I'm just going to leave it like this. This is our first problem. So the rate of change of the area with respect to time t is 8 pi at that particular time instant. So at a particular time, when the radius is 4, this will be the rate of change of the area with respect to time. Okay, let's try example number 2. So we'll erase this. Or example number 3, I guess it is. So we'll try our next problem. So we'll erase. Here we go. Okay, let's set up our next problem. So this is problem number 3. Here we go. Problem number 3. Okay, this is air is pumped into a spherical balloon. So you're blowing up a balloon. It says at a rate of so the air is pumped into a spherical balloon at a rate of 4.5 cubic feet per second. Okay, find the rate of change of the radius when the radius is 2 feet. So find the rate of change of the radius when the radius is 2 feet. So air is pumped into a spherical balloon at a rate of 4.5 cubic feet per second. So find the rate of change of the radius when the radius is 2 feet. So let's start off. Always start off with a diagram or a drawing of some type of sketch. So it don't have to be anything fancy. So you can imagine a balloon. So it's spherical, so it's round like so. Okay, here's a radius. All right. So start off with a diagram. All right, so a little drawing. So here's my balloon. Now it's not much. There we go. Now let's see, what are we given? What do we have to find in this problem? Now what we're given, let's get our given information first. It says air is pumped into a spherical balloon at a rate of 4.5 cubic feet per second. Now let's see, what is a 4.5 cubic feet per second? What are we modeling here? So you got the air coming into the balloon's getting bigger, the volume of the balloon is changing. All right, so when you look at the given information here, now the 4.5 cubic feet per second, okay, that's the rate of change of the volume. All right, so the air is coming into the balloon. That's the rate of change of the volume. So they're giving us dV over dt. So the rate of change of the volume with respect to time is 4.5 cubic feet per second. Find the rate of change of the radius when the radius is 2 feet. So they're also telling us that r is equal to 2. Now, let's see what we got to find in this problem. It says, and it tells us, find the rate of change of the radius, and the rate of change of the radius, that's the dr over dt, okay, when the radius is 2 feet. So in this case, we're trying to find dr over dt. So this is what we're going to have to find in this problem. So once again, given the rate of change of the volume is 4.5 cubic feet per second, and when the radius is 2, what is the rate of change of the radius of the balloon? Now you can imagine, you've blown up a balloon before. Now what happens as you blow up a balloon, okay, the radius increases very quickly at the beginning. Then as the balloon gets bigger and bigger, the radius doesn't increase that much. Now we need a formula that's going to relate the volume of a sphere to its radius. Right? And that's going to be the volume formula for a sphere. So this is V equals 4/3 pi times the radius cubed. Right? So this is our formula we'll have to use with this particular problem. So the volume formula for a sphere is 4/3 pi times the radius cubed. Now we only have the two variables. Now one thing I want to point out, I didn't point this out in the last problem, but when you're doing related rate problems, okay, well, you got to look at your variables and see if all the variables are changing or moving. Now, if the variable is changing or moving, we got to keep that variable. Now, if the variable is not changing, if it stays the same, we can replace it at the beginning of the problem. But if we only have two variables here, the volume is changing, the radius is changing, we got to keep both. But now, sometimes if you have three variables, possibly, you may be able to replace one of them at the beginning of your problem, if that particular quantity is not changing. So if it's held constant, then you can replace it at the beginning of the problem. Now, so to get started, now we got our information we're given. This is going to take the derivative of our volume formula with respect to time. Right now, the derivative of V, this will be dV over dt is equal to. Now, as you take the derivative of the volume formula now, this will be 4/3 pi times r times 4/3 pi times. Now, taking the derivative of r cubed would be 3r squared. You're going to subtract 1 from your exponent times dr over dt. Now, what happens is you multiply 3r squared times 4/3, the 3's cancel out, and we have dv over dt equals 4 pi times the radius squared times dr over dt. Okay, that's the derivative of our volume formula for a sphere. Now I'm going to take the problem down. All right, I'm going to finish this up because it should just be a matter of substituting in now and solving for dr over dt. Now we know that dv over dt is 4.5. Let's put 4.5 in for dv over dt. Let's bring down the 4 pi. Now it says the radius is 2, so when the radius is 2 feet, we plug that in. Okay, times dr over dt. Now, this formula we have to solve for dr over dt. So let's simplify the right-hand side of our equation here. We got 4.5. 2 times 4 gives us 8 pi. This would be r squared, I'm sorry. This would be radius squared. So this would be 4. This would be 4 times 4, which would be 16 pi. There we go. And that'll be dr over dt. So you gotta remember the square, it's the radius squared, not just r. Now, to finish solving this for dr over dt, you gotta divide this side by 16 pi. These will cancel out. That gives us dr over dt on the right-hand side of our equation here. I'm going to divide the left-hand side by 16 pi also. Now I'm going to go ahead and put this in decimal form. Converting this to decimal, I got 0.884. So 0.884. Okay, for the rate of change of the radius with respect to time t. Now this will be in feet per minute. So this will be in feet per minute. Now, one thing I want to point out, if you have a calculator close by, okay, I want you to grab your calculator, pause the video just a second, and divide 4.5 by 16 pi, and see if you get 0.884. Because my students invariably, they don't divide this correctly. Right? So when you grab your graphing calculator here, you do 4.5 divided by 16 times pi. Which gives us, well, let's see, my students tend to get a 0.884, but you got to be careful with this. Because I said this is the answer that my students typically would get when they divide it with their graphing calculator. But you got to be careful. We're going to put the 16 pi in parentheses. So you're dividing 4.5 by the quantity 16 pi. Let's see if we get 0.884 again. All right, so we got 4.5 divided by 16 times pi. Now we've got to put the 16 pi in parentheses. So 16 times pi. And let's see if we get 0.884 again. So let me try this again. Alright, so 16 times pi. Okay, close our parentheses. Gives us 0.0895, so it'll be 0.090. So this actually should be 0.0995. 0.090. Okay, this is it, and this will be in feet per minute. Okay, feet per minute, there we go. Like I said, if you're going to divide this and put this in decimal form using your graphing calculator, make sure you put the 16 pi in parentheses, because a lot of students would have simply got the 0.884, the first answer that I got. So you got to be very, very careful if you convert this to decimal form. Put the 16 pi in parentheses. That's 4.5 divided by the quantity 16 pi. So be very careful if you put it in decimal form. So this will be the rate of change of the radius with respect to time t. Okay, let's try example number 4, and we'll go ahead and erase this. So problem number 4. Erase this here. There we go. Okay, here's the next problem. There we go. to try an airplane problem. All right, so let's try an airplane problem. So this will be example 4. Okay, this is what this problem is asking us to find. Now it says an airplane is flying over top of the house, right? The distance s from the plane to the house is decreasing at a rate of 400 miles per hour. Okay, when the distance is 10 miles. So when the plane is 10 miles from the house, the rate of change, okay, the distance from the plane to the house is decreasing at a rate of change at a rate of 400 miles per hour. So it'd be negative because it's decreasing, right? At a rate of 400 miles per hour when the distance is 10 miles. Okay, what is the speed of the plane if it is flying at an altitude of 6 miles? So let's do this a little sketch. So we always start off with a diagram. You can imagine an airplane flying, going to be flying over top of a house. That's all we're doing. So it's a little diagram. So like so, here's my house. And here goes our airplane. And this will be the distance from the plane to the house. So that'll be the distance from the plane to the house. Now, the height of the airplane will be this side right here, making this a right triangle. So you can see the right triangle formed with the height of the airplane. Now, the airplane is flying in this direction. So to get us started here with our diagram, let's let this, the distance from the house to the plane be s. Let's let this distance be x, and let's let the height of the plane be y. Now, so we'll start our problem off with a little diagram or drawing. And so let's see what are we given in our problem now. So once you got your diagram done, okay, what kind of given information do we have here? So what are they giving us in the problem? Now, so the airplane is flying over top of the house. Okay, the distance s from the plane to the house is decreasing. So the distance is decreasing at a rate of 400 miles per hour. Well, they're telling us the rate of change of the distance of s with respect to time. So the distance from the plane to the house is s. So they're giving us here ds over dt equals. And so this is it's decreasing at a rate of 400, so it'll be negative 400 miles per hour. So they're giving us the rate of change of the distance from the house to the airplane. So that would be ds over dt. It's decreasing at a rate of 400 miles per hour when the distance is 10 miles. So the distance, now the distance would be is s. So when s is equal to 10 miles. Okay. Let's see, what else? What is the speed of the plane when it's flying at an altitude of 6 miles? Now, let's see that altitude of 6 miles. Now, y would be the altitude, wouldn't it? So y is equal to 6. Now, what do we have to find? So I think that's all the information we're given. It says when the distance, says what is the speed of the plane? So the speed of the plane, so that'll be the rate of change of the speed. Now the airplane is flying in this direction here. So the rate of change of the rate of change of the speed of the plane, or the speed of the plane, would be the rate of change of x, not y. Remember, the airplane's not going up and down; it's going straight parallel to the ground, right? So x is what's changing here. So this would be, in this case, we're going to have to find, okay, dx over dt. So that's what we got to get here. So we're trying to get dx over dt. Right? So that would be the rate of change, the speed of the plane. Also, we got to remember now, okay, speed can't be negative. This is the absolute value of velocity. Right, so what we're going to get here is the velocity now, and if it's negative, we got to make it positive. So remember, speed cannot be negative. So if we get a negative answer, we got to change the sign on it here. All right, now, okay, once we've got our given information, we know what it is we're trying to find now, right? We're trying to find the rate of change of x with respect to time. Because as the airplane flies over top of the house, x is what's changing. Now, we need an equation or a formula now that's going to relate the three sides of this triangle now. Now, we're not talking about the area of the triangle, we're talking about the sides that are changing. So, first of all, let's notice something real quick. As you look at a triangle, the three sides of a triangle, we're not talking about any angles really, it's going to be a right triangle, right? As the airplane flies towards the house, it's still going to be a right triangle. Now, when you're relating the sides of a triangle, you know, how about the Pythagorean Theorem? A squared plus b squared equals c squared. In our case, it would be x squared plus y squared equals side s squared. Now, so we use the Pythagorean Theorem as our equation or our formula this time. Now, we got three variables here. Now, let's make sure that we need all three variables. 3 variables are much more difficult to work with than 2. So if we can get rid of one of them, we want to get rid of it. All right, so first of all, let's see if, as you look at our triangle over here, the airplane is flying over top of the house. Let's make sure that X, Y, and S are all changing. So let's see if all of them are changing. Now, first of all, X is changing. So as the airplane is flying over top of the house, X is changing. Now, Y is not changing. So the height of the airplane's not going up and down. It's flying straight. Right? So it's flying straight. So the height of the airplane is not changing. So we don't need Y in our formula. Now it says Y is 6. So Y is always 6. I mean, the airplane's not getting any lower, right? So that would be 6 miles. So 6 miles. So let's see if we can replace Y in our formula. So x squared plus 6 squared equals s squared, or x squared plus 36 equals s squared. So this is our equation now. So that's at the very beginning of your problem, all right? If you have a variable that's not changing, it's constant, go ahead and replace it right now. So only those variables that are changing we need to keep. Now, this is our equation. This is the Pythagorean Theorem, basically. Let's take the derivative of x of all 3 terms, and let's see what our derivative will be. Now, let's take the derivative of x squared. Remember, now you're using implicit differentiation. You're going to take the derivative of x with respect to time. So the derivative of x squared would be 2x, okay, times dx over dt. Now, the derivative of 36 is 0, right? So you're taking the derivative of a constant. Well, that's 0. And the derivative of s squared would be 2s times ds over dt. Now, I'm going to take our problem down here, so we'll move it out of the way. All right. Now, it should just be a matter of substituting in. So let's substitute the 0 here. We can just drop. I'll just erase that. So this is our equation. 2x times dx over dt equals 2 times s times ds over dt. So let's do the x. So substituting in for x. But if you notice in this problem, they don't give us x. But we need it. So to get x, let's go back up to the original triangle relationship. And if you look at your triangle again, okay, this side is 6. S is 10. Okay, what does x have to be? So whenever the distance from the airplane to the house is 10 miles, the height of the airplane is 6. Okay, what does this distance along the ground have to be? Now, once again, we're working with a right triangle, right? Now, so to get x, let's just use the Pythagorean Theorem. A squared plus b squared equals c squared. So in this case, x squared plus 6 squared equals 10 squared. Right, so let's use our Pythagorean Theorem to get x. So we have x squared plus 36 equals 100. X squared is going to be equal to 100 minus 36. Let's see, we'll bring this up here. This is the x squared equals 64. Take the square root of both sides. X is equal to 8. So you write this in here too. So x is equal to 8. So we can substitute 8 in for x now. So if one of your variables is missing like this, typically you can find it by going back up to the original relationship. In this case, it's pretty easy to find. You're just using the Pythagorean Theorem. So when the distance is 10, the height of the airplane is 6, then the distance along the ground has to be 8 miles. So erase this here. So it has to be 8 miles. So it'll be 2 times 8 times dx over dt. Now dx over dt is what we're trying to get. That has to be equal to 2 times s. Now s is 10. And ds over dt is negative 400. So we substitute everything in. We know what x is now. We know what s is. S is 10. And the rate of change of the distance from the plane to the house is negative 400. So we'll plug that in. Now we got to solve this for dx over dt. Now first of all, let's simplify the left-hand side. 2 times 8 is 16. Dx over dt, that'll be equal to, now as you multiply here, this will be negative 800. So negative 800 divided both. Now to solve for dx over dt, we're going to divide this side by 16. Divide this side by 16. We're going to do dx over dt. So the rate of change of x, that's the rate of change of the, as an airplane is flying towards the house, is equal to negative 8,000 divided by 16, which would be negative 400 miles per hour. Now, keep in mind, negative 400 is the velocity now, right? This is the velocity. We're looking for the speed. So the speed should be equal to positive 400 miles per hour. So be careful. Remember, speed cannot be negative. Right? Velocity can be, but speed can. So the speed is 400 miles per hour. Okay, so this is our, this is a pretty good little problem. I like this. You got the Pythagorean Theorem. You got that. A lot of times when you have a triangle relationship like this, you can use the Pythagorean Theorem if the sides are moving like this. Okay, let's try another problem. So let me erase this one here real quick. Okay, there we go. The related rates. So we got one more to do. So one more problem. Okay, let's try problem number 5. Here we go. Problem number 5. Right. Okay, this is our cone problem. It says a conical tank is 5 feet across the top and 12 feet deep. If water is flowing into the tank at a rate of 10 cubic feet per minute, find the rate of change of the depth of the water when the water is 8 feet deep. So when the water is 8 feet deep. So a conical tank is 5 feet across the top, 12 feet deep. The water is flowing into the tank at a rate of 10 cubic feet per minute. Find the rate of change of the depth of the water when the water is 8 feet deep. All right, so here's our problem. Now first let's start off with a diagram. Right? So we always start off with a diagram. Right, so let's see, we're talking about a cone. So here's our cone. Like so. So here's our cone. And it says the cone is 5 feet across the top. So actually, let me change this here. This should be 10 feet across the top. So it should be 10 feet. So make a little change on that. So it should be 10 feet across the top. So 10 feet across the top and 12 feet deep. Okay, the water flowing in the tank is 10 cubic feet per minute. Find the rate of change of the depth of the water when the water is 8 feet deep. So make a little change there. Okay. Now, so to start off, we got our, I guess, a little diagram. Let's see, it says, so 10 feet across the top. Erase this, so 10 feet this way. Right, so 10 feet across the top, so that will make the radius, okay, 5 feet. And let's see, it's going to be, what, 12 feet high. Now, so that'll be the height of the cone. And let me draw the height inside the triangle here, too. Or inside the cone. All right, now let's see what are we given in this problem now. So what are we given? So the conical tank is 10 feet across the top, 12 feet deep. The water is flowing into the tank at a rate of 10 cubic feet per minute. And let's see, find the rate of change of the depth of the water when the water is 8 feet deep. So let's see, we're given. Now first, it said the water is flowing into the tank at a rate of 10 cubic feet per minute. Now, 10 cubic feet per minute, water flowing into the tank, that's the volume that's changing. Right? So they give us the rate of change of the volume with respect to time. So we're given dV over dt, that'll be equal to 10 cubic feet per minute. Okay, also it says when the water is 8 feet deep, now that would be, when the water is 8 feet deep, that would be the height. So the height would be 8 feet. Okay, let's see what else. What are we trying to find here? What are we looking for here? So what are we asked to get? Okay, so if the water is flowing into the tank at a rate of 10 cubic feet per minute, find the rate of change of the depth of the water. Now the depth of the water would simply be the height of the water, right? So that would be h. So it would be dh over dt. So in this case, they're asking us to find the rate of change of the height. So you can imagine the water flowing into the tank and the height is increasing over time. Right. Now also notice something as you look at a tank like this. You've got an empty tank and you start filling it up with water. Right? You start filling it with water. At the beginning, the radius increases quickly. Right? Then as the water in the cone gets higher and higher and higher, the radius doesn't increase as fast. Right? So the rate of change over time of the radius isn't going to be as fast as it was at the beginning when you first start pouring water into the cone. Right? So at the very beginning, the radius will increase quickly, and then not so fast over time as the water level increases inside the cone. Now we need a formula now, or an equation, if you will, to relate the volume of the cone and its height. Well, if you remember from geometry, the volume of a cone is 1/3 pi times the radius squared times its height. All right, so this is our volume formula for a cone, and this is what we're going to have to take the derivative of. All right, so to find dH over dt. Now here's a problem with a volume formula for a cone. Now this has 3 variables in it. Now 3 variables. So remember, we don't want 3 variables unless we absolutely have to have 3 variables, right? First of all, let's make sure that all 3 variables are changing. Let's see if we can replace one of them at the very beginning. Because remember, the diameter, the radius is 5 and the height is 12. So let's see if there's one of these that we can replace. Now, first of all, water's flowing into the tank, so the volume is changing. We got to keep, of course, we have to keep the volume, right? Okay, what about the radius? Now, as the water level increases inside the tank, well, the radius is changing also, so we got to keep R. We got to keep the radius. Okay, what about the height? Surely, as the water level increases inside the conical tank, the height is changing also. So all 3 variables here are changing. So the radius is changing, the height is changing, and of course the volume is changing. So we need to keep all 3 of these. Now, if we take the derivative, that means using the product rule. You look at this side of your volume formula, 1/3 pi times the radius squared times h. That's r squared times h. That's the product rule. But there's a little trick that we can use that works specifically with cones. All right? Notice in this problem, they told us that the cone was 10 feet across. That's a radius of 5 and a height of 12. Okay, we can replace the radius in this particular formula. Now, I'm going to show you how we can do it. If you look at our diagram here, so let me erase this here. Now, if you look at our diagram, you see the right triangle here inside our cone. Okay, at a particular time, so the height of the cone is 12 and the radius is 5. Well, inside the cone here, we have another little right triangle. I'm going to make me another little right triangle. This is R and this is H. So what I have here, I've got a little right triangle inside of a bigger right triangle. So we have basically, if you remember from geometry, 2 similar right triangles. So let me bring this out here. So you got the big triangle. Okay, this is 5 and this is 12. And then you got the little triangle inside the big triangle. Like so. This is R and this is H. Now we can use the fact that we have 2 similar right triangles inside the cone to replace the radius in our formula. Let me show you how you do it. Now remember, now similar triangles, your sides are going to be proportional, so let's set up a little proportion using our corresponding sides. Now let's see, I'm going to do, I'll do 5 over R equals 12 over H. Okay. Now, we can solve this for either R or H. Now, we got to keep H. Remember now, we're looking for the depth of the water, so we have to keep H in our formula, which means we're going to replace R with an H expression that means the same thing. So let's see if we can solve our little proportion here for R in terms of H. So cross multiply. Cross multiply gives us 5H equals 12R. All right, so cross multiply. And let's see, we need to keep H. So we're going to divide this side by 12, divide this side by 12. We end up with 5 over 12 times H equals R. So it's a little equation that relates the height and the radius of our cone. So here's what we're going to do now. Let's make a little substitution. Let's replace the radius with 5 over 12 times H. Okay. And so this works specifically with cones. So our volume formula now becomes 1/3 pi times the radius squared. So the radius, we're going to substitute 5 over 12 H. 5 over 12 times H squared times the height. Now, by substituting in, now we have a volume formula in terms of V and H only. So only 2 variables. We don't have to use the product rule now. To use the product rule with this problem, we would have had to have been given some more information. More information than what we're given here. All right, so this is our problem. So now, before we take the derivative, we need to simplify this a little bit. And let's see how this will simplify now. So V equals 1/3 pi. Now, 5 over 12h quantity squared, we're going to square the 5, would give us 25 over 144 times the height squared times h. So go ahead and square the 5, the 12, and the h inside our parentheses. So we end up with 25 over 144 times the height squared times h. And to simplify our formula some more, we have 1/3 pi. Well, I'll tell you what, let's go ahead and multiply here too. Let's go ahead and multiply. The 1/3 times the 25 over 144 gives us 1 times 25 is 25, 3 times 144. Now 3 times 144 is 432 pi. Now h squared times h is h to the 3rd power. Okay. Now this is really the key part of the problem, is replacing the radius with the 5 over 12h and then simplifying. So now here we've got our volume formula. We're ready to take the derivative now. We've got to simplify it. The volume is 25 over 432 pi times the height cubed. Okay, let's see what we get for our derivative. And I'm going to take the problem down. Let's set this over here again. Okay, let's take the derivative of the volume with respect to time. So that'll be dv over dt. That'll be equal to. Now, as you take the derivative of the right-hand side, now you're going to multiply 3 times 25 over 432. And you basically go multiply the 3 and the 25. That gives us 75 over 432 pi times the height squared. So remember to subtract 1 from your exponent now when you take that derivative there, times dh over dt. So you got to remember, every time you take the derivative of a variable here, you have to leave dh over dt. This is implicit differentiation. Okay, now it should just be a matter of substituting in and then solving for dh over dt. Now, dv over dt is 10. That'll equal 75. I'm going to put the pi with the 75. So it'll be 75 pi over 432 times the height squared. Now the height is 8, so it'll be 8 squared times dh over dt. Let's see, simplifying this some more. 8 squared would be 64. 64 times 75 would be 4,800. So we have 10 equals 4,800 pi divided by 432 times dh over dt. Okay, so we got the right-hand side simplified. Now, to solve this, to finish solving this for dh over dt, I would simply multiply the reciprocal. See this big fraction here? Let's multiply the reciprocal to both sides. And on the right-hand side, we'll multiply 432 over 4,800 pi. And these two are going to cancel out. On the right-hand side, let's do the same thing up here, 432 over 4,800 pi. And let's see, and as you multiply to 10, as you multiply to the top of your fraction here, it'll be 4,320 over 4,800 pi. Now that'll be equal to dh over dt. And let's see, this will reduce to 9 divided by 10 pi. So dh over dt should be 9 over 10 pi. Now this will be in feet per minute. Okay, now let's see who remembers now from the last problem. Go ahead and, if you have a graphing, if you have a calculator close by, go ahead and divide 9 by 10 pi. And I'm going to do the same thing here. You got to remember now, as you divide this, you got to put the 10 pi inside your parentheses, right? So 10 pi inside your parentheses. So 9 divided by 10 times pi. So 9 divided by quantity 10 times pi gives us 0.8286. So 0.286 over 0.286 feet per minute. So I believe that's our units, so 0.286. And there we go. That's the last of our 4 problems. Now my students will be looking at some more problems in class, but this is 4 good examples, classic examples if you will, and to give us some idea as to how related rates are used in the real world, right?